Hello, thank you so much for joining this talk. My name is Sahar, and I'm going to present our paper, Adversarial Watermarking Transformer towards tracing text provenance with data hiding. This work is done in collaboration with Mario Fritz. Recent language models such as GPT-2 have shown a great performance with high-quality output text. They were able to generate entire articles that seemed very convincing for human evaluators. An even more powerful and larger model was later released. This raised significant concerns about the implication and potential abuse of such models. As a countermeasure, these models were released in a staged release or only made available through a commercial black box API. Active and protective release strategies are still lacking. Current passive defenses, such as classifiers, depend on the generation configuration in the language model, which is not sustainable in the long run. Therefore, we study language watermarking as an active and sustainable solution for generation models abuse. Our envisioned scenario is as follows. The owner of a black box text generation API watermarks the language model's output. Then, an adversary uses the watermarked API to generate malicious content at scale, such as fake news or misinformation. News platforms can now cooperate with owners to decode the watermark and detect machine-generated text. This way enables the responsible release and the potential regulation of AI technologies and generation models. Towards that goal, we propose the Adversarial Watermarking Transformer, or AWT in short. Our model is the first end-to-end method for language watermarking. It consists of a data hiding network to generate the watermark text and a data revealing network to decode the message. We utilize adversarial training to achieve stealthiness and subtle encoding of the information. All these components are jointly trained. We don't use any paired training data, and the model learns to encode the information automatically. We define three evaluation axes for the language watermarking task. The first one is effectiveness. This is concerned with successful message encoding and decoding. At the same time, it measures text preserving and introducing minimal perturbations to the text correctness and semantics. The second one is secrecy. Ideally, watermark text should be indistinguishable from non-watermark text. This is a proxy for the naturalness of watermarking, and it also helps to avoid detection and removal attempts. The last one is robustness. This means that the watermark should be highly resilient against removal attempts. These axes could be competing, and the watermarking scheme should achieve a good trade-off between them, which we empirically show in our paper. Unlike deep learning methods and images, previous work in language watermarking mainly relied on rule-based methods, such as synonym substitution or structural changes. However, these approaches might change the input sentence to a large extent. Also, they use fixed changes, which results in limited flexibility and can also compromise secrecy and robustness. Our work addresses these limitations. Now we will present more details about our method. AWT consists of a data hiding network, a data revealing network, a discriminator, and other complementary losses. The backbone models are transformer encoders or decoders. We start with the data hiding network, which is a sequence-to-sequence model consisting of an encoder and a decoder. The encoder takes the input text and the input binary message and produces a shared embedding of them, which will be passed to the decoder. The decoder generates the watermarked sequence. Since we don't use any paired training data, the model is trained as an autoencoder to reconstruct the input text. We jointly train a message decoder that takes the one-hot encoded watermark sequence and reconstructs the message. The message reconstruction loss is the binary cross entropy over all bits. Balancing these losses achieves a trade-off between text preserving and message reconstruction. Encoding the information can be done in an obvious way that compromises secrecy and robustness. To avoid that, we utilize adversarial training and train the data hiding and revealing networks against a discriminator. It takes the watermarked and non-watermarked sentences and should classify between them. Finally, to achieve better output quality, we use additional losses as a fine-tuning step. We maximize the likelihood of the generated sequence under a pre-trained language model. This step helps to maximize the syntactical correctness. We also utilize a pre-trained sentence embedding model. We minimize the distance between the input and output sentences embeddings. This step helps to achieve more semantic consistency. We now move to our experimental evaluation, and we start with describing our setup. We use the word-level Wikitext tool that's curated from Wikipedia articles with live processing. To evaluate the output, we use three metrics. The first one is the meteor score to find the overlap between the input and output text. It ranges from 0 to 1, indicating no to perfect similarity. Meteor is usually used in machine translation tasks to evaluate against a ground truth sentence. However, we found that Meteor is not enough for semantic evaluation. Therefore, we use the pre-trained sentence word model to evaluate the semantic similarity. We compute the L2 distance between the embeddings of the input and output sentences, where lower distance is better. These two metrics measure the text utility or quality. Finally, we evaluate the bit accuracy of decoded messages over all sentences in the test set. We use a message length of 4 bits, sampled randomly during training. We encode a message per sentence or a text segment. Our main scope is an article-level watermarking. To enable that, sentences can be successively encoded with a sequence of messages to form a long watermark. Messages can be decoded from each segment independently. To verify the watermark, we can find the number of matching bits against the original long watermark sequence. To allow soft matching, we use hypothesis testing based on the number of matched bits, where the null hypothesis is the chance level matching or the no watermarking case. We now examine the different evaluation axes, and we start with the effectiveness. We first evaluate the effect of each component in the model. Adversarial training helps to preserve the semantics, which is indicated by a lower S-spread distance. Additionally, fine-tuning with the auxiliary losses helps to further improve the utility or the semantics. For all variants, bit accuracy is very high, indicating successful decoding. We then study further techniques that could improve the utility or the output quality. The first one is sampling. We sample different sentences for each input. Then we select the best sample based on a quality metric such as language model likelihood or S-spread distance. The second one is selective encoding. If the perturbation done by watermarking is higher than a threshold, the sentence can be left non-watermarked. This will result in a random chance matching for this sentence. The decoder side can attempt to decode the watermark from all sentences without knowing which ones are watermarked. The decision is then based on the total matching accuracy. By changing the threshold or the number of samples, we can increase the text utility, which is indicated by higher meteor scores and lower S-spread distances. However, this has a trade-off relationship with bit accuracy. This can result in different operating points of utility versus accuracy. As previously mentioned, the verification is done on an article-level input by null hypothesis testing. The watermark is detected or verified if the p-value is less than a threshold. We evaluate the watermarking detection rate and its relationship with text length. We perform this analysis for different operating points of accuracy and at two significance levels. Increasing the text length increases the watermark detection rate even when using lower accuracy operating points. We also validate that real text or non-watermark text has random chance matching, which results in a high p-value and low false positive rates. Please refer to the paper for other decoding strategies. We now show some qualitative examples of different models variants. We first show the no discriminator model. This variant performs systematic fixed changes, and it uses less likely tokens. This affects the secrecy and robustness, and it also affects the text semantics. Adding a discriminator, but without fine-tuning, helps to have a better output. However, it still had many mistakes. We finally show examples of watermarked sentences using the full model. We observe that the changes are all from common tokens without fixed changes. The correctness and semantic consistency are also greatly improved. We still observed cases where the model made mistakes, indicating that there is a room for further improvement. We now evaluate the secrecy of the watermarks. We first evaluate and visualize the word replacement patterns done by the model at scale. We here show the pairwise transitions between the most commonly used words by the model. Since the diagonal elements have high values, it means that these words are not constantly replaced. Additionally, we don't observe any sparse or fixed transitions between pairs. These observations suggest high flexibility and concealing of the encoding. We then evaluate the occurrences counts of the most likely words. Compared to non-watermark text, our model keeps the count of these top words comparable. This is in contrast with the no discriminator model that can cause clear statistical artifacts. We then train independent binary classifiers to discriminate between non-paired watermarked and non-watermarked text. Ideally, the F1 score of the classifiers should be at random chance, indicating high secrecy. We examine different model variants and different classifiers. The no discriminator model has a very high F1 score, indicating poor secrecy. Increasing the naturalness of the watermarks helps to have higher secrecy. Therefore, the full model had a close to random chance F1 score, as required. We then examine the robustness of watermarks. The attacker's goal is to remove the watermark with minimal changes to the text in order to still have high utility. Therefore, we study the relationship or the trade-off between bit accuracy drop and the S-per distance increase with respect to the original sentence. We examine two categories of attacks. The first one is basic attacks. Here, the attacker knows about using a translation-based watermarking scheme, but not the model details. The second one is advanced adaptive attacks, in which the attacker has full knowledge about the model, but no white box access. We consider two basic attacks. The first one is denoising. Here, the attacker applies random noise to non-watermark text. Then, they train a denoising autoencoder to remove the noise. The DAE is then applied to the watermark text before decoding. This attack assumes that the noise would approximate the watermark. Based on this assumption, we hypothesize that improving the quality would make denoising less effective. We validate this hypothesis by applying the attack on the three model variants. We observed that the full model had a small drop in accuracy compared to the lower quality no discriminator model, which empirically confirms our hypothesis. The second attack is random changes. We apply random word removal and replacement with a certain probability. We study another variant where random changes are coupled with denoising to have a smoother output. We observe that random changes cause high degradation to the output while less significantly affecting the accuracy. Advanced adaptive attacks assume that the attacker can train their own watermarking model that's only different in the random initialization. Our first attack is re-watermarking. The attacker inserts a random watermark using their model. The goal of this attack is corrupting the original watermarks and confusing the first model decoder. We observed that two independently trained models can use different patterns to encode the information, and therefore the accuracy of the original watermarks didn't drop to random chance despite having a strong adaptive attack. The second attack is de-watermarking, and instead of perturbing the text with adding a second watermark, the adversary could train a de-watermarking model. We train a denoising autoencoder on the input and output pairs of the second watermarking model. The DAE is then applied to the output of the first watermarking model. We observe that the drop in bit accuracy is similar to re-watermarking. We again attribute that to the differences between the two models. However, de-watermarking has a less perturbation effect, which makes it relatively the most effective attack among the attacks we studied. Yet, it is the most computationally expensive one. Please refer to the paper for more details and examples about attacks. Finally, we evaluate our model against baselines. We implement a synonym substitution baseline based on a previously introduced watermarking method. In summary, we replace a word with this synonym. We partition the synonym set for one word to two groups and assign different bits for each group. The decoding is then done by lookup tables. Our method achieves higher flexibility and a significantly better trade-off between the different evaluation axes. It also has higher resilience to attacks. We then compare the two methods against non-watermark text using a user study. We asked users to rate the quality of sentences from 0 to 5. We show that our method had higher ratings and is closer to the rating of non-watermark sentences. To conclude, we study language watermarking towards moving from passive to active defenses against deepfakes that are more sustainable. We propose the first end-to-end language watermarking scheme. Our model achieves a significantly better trade-off between the evaluation axes compared to a rule-based baseline. Our work opens new research directions of automatic language watermarking towards improving the quality and robustness of watermarks. We hope that our work raises follow-up research and discussions on the responsible release and regulation of AI and text generation technologies. Our code and models are currently available. Thank you so much for listening, and I'm looking forward to the discussion.